Now let's look at how to do complex arithmetic. So addition and subtraction of complex numbers is fairly straightforward when the numbers are in Cartesian coordinates. However, it cannot be easily done when they're in polar coordinates. And in fact, I would assume that in most cases, given polar coordinates, people probably convert those to Cartesian coordinates and then just add them. So it's really like adding polynomials. You just add the like parts. So if I have z1 is equal to x1 plus jy1 and z2 is equal to x2 plus jy2, you just add the real parts and then add the imaginary parts. So here's z1, here's z2, and so the real parts are x1 and x2, that's this, and the imaginary parts are jy1 and jy2, that is this with the j factored out. And subtraction is similar to that, right? Now I'm subtracting the real part of z2 from the real part from z1 and subtract the imaginary part from z2 from the imaginary part from z1. Multiplication is like multiplying two polynomials, so I just use the FOIL method, first inside, outside, last. So I multiply these two numbers together. I have x1 times x2 is this, x1 times jy2 is this, jy1 times x2 is this, and jy1 times jy2 is this. Now remember, j here is the imaginary number, square root minus 1. So when I square it, I actually just get -1. So the product of these two imaginary numbers is a real number, with the sign now changed here. So now I have a real number here and a real number over here. So x1, x2 minus y1, y2 is this. And then I just add the two imaginary parts and get this. In polar coordinates, though, it's even easier. When I multiply z1 times z2, I have r1 times r2 times e to the j theta1 plus theta2 power. Now this may look sort of magical, but imagine this was x squared and this was x cubed, and I was multiplying those together. Well, then I would add the powers, right? I would have x cubed times x squared is 3 plus 2 is 5. I would just add those. That's all I'm doing is here, adding the powers. And then I happen to factor out the j to make it a little easier to read. Division is the most complex. In Cartesian coordinates, I have this, z1 over z2. But the problem is, if I try to simplify this, I can't really do it with the denominator being a complex number. So the solution is to multiply the numerator and the denominator by the complex conjugate of the denominator. Right? So what is that? Well, the denominator here is x2 plus jy2, so the complex conjugate will be x2 minus jy2. If this had been a minus here, then we would have a plus in the complex conjugate. So now I take this right here, and I multiply it by x2 minus jy2, the complex conjugate of this, over x2 minus jy2. This is just 1, right? Some complex number divided by that same complex number, so it's 1. And then when I multiply the numerator values, it's just multiplication of two complex numbers, so I get this expression here. But the reason why we did this is so that way when we multiply the denominators, the imaginary parts cancel out, leaving only a real number. And now I can simplify. I can have this real number divided by this real number. If I knew what x2 and y2 were, I could simplify, but I can't do anything beyond that without knowing. But I could have this real number divided by this real number plus j of this number divided by this number to simplify. That's in Cartesian coordinates. In polar coordinates, it's easier. So here's z1, here's z2, and so I just divide r1 by r2, and just like I would if I had, say, x to the 5th power divided by x squared, I would say the 5 minus the 2 gave me x cubed as the answer. Well, here I subtract the power of the denominator from the power of the numerator. It's really just that simple. So now let's do an actual example by hand to hopefully make this more clear. So here I have two complex numbers, right? And let's see what these would be in polar coordinates. So for polar coordinates, to get r, I'd have square root of 2 squared plus 3 squared. And then I would have e to the j arc tangent of 3 divided by 2. And this simplifies. I'm copying this from a piece of paper. That's how I know, because otherwise it'd be somewhat painful. 3.61 times e to the j, 0.98. All right? And this is radians. For this number, this becomes square root of 4 squared plus minus 2 squared, e to the minus j, 4 divided by minus 2. And this simplifies to 4.47 e to the j minus 0.46. So where's this vector at? Well, here's our 4 was over here. Our minus 2 is here. So this. So it's really this angle here is what I just calculated in radians. Right? Now, if you want to, you could add 2 pi to this to get 4.47 e to the j 5.8. Because 2 pi would be 2 pi is approximately equal 2 times 3.14, which would be equal to 6.28, right? So it's less than that because we didn't quite make it all the way around. So I did that so we can check our work. Now if I want to add these, it's straightforward. It is 2 plus j3 plus 4 minus j2. So 2 and 4 is 6, and 3 minus 2 is positive 1. So you can write this way or whatever you want to do on that. All right? So I have a multiplication. z1, z2 would be equal to 2 plus j3 times 4 minus j2, and this becomes 8 minus j4 plus j12 plus 6, which is 14 plus j8, right? And it's equal to square root, this is in Cartesian coordinates, in polar coordinates, it's about 16.13 e to the j 0.52. All right. If I'd done this in polar coordinates, since I produce these values, and I should pull, sorry, I should pull the 4.47 out to the beginning. It would be easier. That's a 5/8. So I had to do some rounding off between the two. So here I actually got 16.14 on my calculator and EJ 0.52. So they're the same. So whether I did it, took the values in polar coordinates and did it, or kept it in Cartesian coordinates, did it, I get this right here. Now what about the division? So this would be Z1 times Z2, and sometimes you write the complex conjugate with the star. Some people use a bar. Divided by Z2 times Z2 star. Remember the complex conjugate of the denominator. So the denominator was this, 4 minus J2. The complex conjugate of that now as a minus becomes positive. And if we cut right to it, this becomes 2 plus J16 over 20, which is equal to 0.1 plus J 0.8. And in polar coordinates, this value right here is square root of 0.1 squared plus 0.8 squared times e to the j arctangent 0.8, 0.1, which would be equal to 0.8 e to the j 1.44. If I'd done it in polar coordinates to begin with, so I have 3.61 divided by 4.47, which is about 0.8. And then I have 0.98 minus a minus 0.46. So it's actually going to be greater than 1. And with some rounding off, I got about the same thing. All right? So there's how to work it out by hand.